All right, so today I want to start out with just some information about units, unit conversion. It's stuff that probably a lot of you, most of you have dealt with before, but I just want to make sure it's in your notes, and maybe there's some people who are sort of rusty on this kind of stuff. So any scientific measurement has units. In this class, that's right. Every unit that we're dealing with can be written as a combination of three basic unit types. So every unit can be expressed as a combination of three basic unit types. Those are length, I spelled that wrong. Length, time, and mass. And we'll use those to come up with a couple of other combinations of units, like units of velocity, acceleration, energy, force. So this list can go on and on, but the key thing is that everything in this class, so velocity is a length per time. Force is length, why did I pick that one? Length per time squared times mass. And so this is all you need. And then in physics 2, you'll deal with some other basic types like charge. Maybe that's the only other one. Mostly, we're going to do all our calculations in SI units. That stands for International System in French. I'm not going to try to pronounce that, but SI units. It's like Système International. It sounds better if you're smoking, if you're drinking coffee and smoking. So in SI units, the length measurement is meters. That's abbreviated lowercase m. The time measurement is seconds. That's a lowercase s. And the mass measurement, the mass unit is kilograms. You might think it would make more sense if it was grams because this has that prefix of kilo on it, but this is just how it's done. So, and the abbreviation is lowercase kg. So everybody, even before you take any science classes and stuff, you're used to basic unit conversions. So you're already used to simple unit conversions. Like, for example, how many inches are there in 3.5 feet? And to do this, we're going to use the fact that 1 foot is equal to 12 inches. And so intuitively know that the way to do this is to start with that 3.5 feet, multiply it by 12 inches, you get 42 inches as the answer. But let's just come up with a systematic way of doing this. It'll work for these simple ones, but it'll also work for the ones that you can't easily do in your head. And so what we're going to do is so our approach is we're going to multiply the original quantity by a ratio that's equal to 1. Well, I just said that 1 foot is equal to 12 inches. So if you take the ratio of 1 foot over 12 inches, that has to be equal to 1 if you divide something by itself. And that's equal to 1. And you can also take the reciprocal of that. That would be 12 inches over 1 foot. So our approach is we're going to multiply 3.5 feet by one of these two ratios. And the question is, which of those two? So which one of these two ratios? We want to choose the ratio that cancels the unwanted units. We're already in feet, and we want to get rid of feet. We just want to express our answer in inches. And so we'll take 3.5 feet and we'll multiply that by, we want the one with feet in the denominator, so it cancels the feet in the numerator here. So 12 inches is equal to 1 foot. And now you can just do the math as if these units are algebraic variables. The feet here cancel the feet there. And you come up with 3.5 times 12, or 42 inches, which is just what we got, just thinking about it. This approach will work with more complicated things too. If you're converting stuff that's like meters to the fourth over kilograms times seconds, you're trying to convert that to, feet to the fourth, blah, blah, blah. That you can't do in your head, but this approach will still work. And just to save a little time, because sometimes these are sort of cumbersome expressions, I'm going to write it in this format, 3.5 feet. There's the fraction bar. And these vertical lines are just showing where the parentheses end and begin. So 3.5 feet times 12 inches over 1 foot means the same thing as what I have above. Then you can cancel the feet. And it comes out the same way. Any questions about that? Okay, so now let's do this with combinations of units. The idea is the same. You just have to do multiple steps. So let's say that we want to convert I don't have the one I'm thinking of here, but let's say we want to convert 9.81 meters per second squared into units of feet and minutes. And we're going to use the conversion factors that 1 meter is equal to 3.281 feet, and that 1 minute is 60 seconds. First of all, what's the final combination of units we're going to get? If we're starting with meters per second squared and we're re-expressing it in feet and minutes, what's our unit going to be? It's going to be feet per minute squared, because you always have to go from, if this is length per time squared, you have to end with length per time squared. Anybody happen to know what the significance of 9.81 meters per second squared is? Yeah, if something's in free fall, no matter what it is, we're going to talk about that a lot, then that's the acceleration, 9.81 meters per second squared. So it starts out at rest and speeds up downwards at that rate. Okay, so we'll start with, excuse me, start with 9.81 meters. And here's this fraction bar. And then in the denominator, we have seconds squared. I'm going to write that as seconds times seconds. And just one by one now, each column, each ratio is going to convert one of these basic units into the new basic unit. And eventually we'll have them all converted and then we're done. So I guess I'll do meters to feet first. 1 meter is 3.281 feet. So we're going to either have 1 meter over 3.281 feet or the reciprocal of that. We want to cancel the meters. So that means the meters have to be in the denominator. We have 1 meter there, 3.281 feet in the numerator. Now we've gotten rid of the meters and our units of length are feet. So that's good. We're on our way. We still have the seconds times seconds, so we have to deal with that now. So first I'm going to do this first second. 1 minute over 60 seconds or 60 seconds over 1 minute. To cancel these seconds in the denominator, we need the seconds in the numerator with what we're multiplying by. 60 seconds over 1 minute. And that cancels one of these, but not the other. So if we multiply these numbers out now, we'd have units of feet per second times minutes, which is that's a unit of acceleration, but not the one that we're looking for. So we have to do one more cancellation. So I'm going to do the same thing again, 60 seconds over 1 minute. And now we're done. The units that are left are feet per minute squared. I don't have this number. Anybody have a calculator? Can you tell me what that number is? It's going to be something really big. 872 feet per minute squared. Okay, so if you want to use those unusual units, that's the acceleration of gravity.
So for that case, if you try to cross out the seconds, you have to have additional 60 seconds over 1 minute. If that case.
Yeah. So right, you have to deal with another way. You could think of it this way too. You could think of it as 9.81 meters over seconds squared. And then we'll convert this 3.281 feet over 1 meters. Well, they're multiplied together, but yeah, you could think of this as 60 seconds squared over 1 minute squared, and that's the same thing. So whichever one of those you like, use that. But just notice that you have to square that 60. If you don't do that, you get the wrong answer. Any other questions about this? Um, so let's use this to answer this question. Let's say that we have a cubic meter. So this is a cube. Every one of these lengths is 1 meter. And let's say it's divided up into, or let's say that it's, think of it this way, it's an empty box, this big empty box. And now we're going to carefully fill this empty box with little centimeter cubes. You follow what I'm getting at here? So these are 1 centimeter cubes. How many of these little cubes fit in this big box? So the way we're going to do this is we're going to start with 1 cubic meter. Okay, that's what we're starting with. And then we're going to use the fact that 1 meter is 100 centimeters. And we have to do that cubed. So I'll do it that second way I showed. 1 meter cubed is equal to 100 centimeters cubed. So this cancels with this. And you're left with 100 to the power of 3. That's 1 times 10 to the 6 centimeters cubed. So there's a million of those. And that's just the shorthand I'm going to use. That's how you enter this into a calculator. But what I mean there is 1 times 10 to the 6 cubic centimeters. Any questions about that? Okay. And then also, we're going to use a lot of prefixes, like kilograms is grams with kilo in front of it. So I'm going to just give you the most common of those. So I'll call these unit prefixes. So first, nano, we'll think of that as meaning times 10 to the minus 9th. So each one of these is just going to be equal to a factor. And I'm just going to tell you what that factor is for each one. The second one is micro. That's times 10 to the minus 6. The third one is milli. That's times 10 to the minus third. The fourth one is centi. That's times 10 to the minus 2. The fifth one is kilo. That's times 10 to the positive third. Sixth one is mega. That's times 10 to the sixth. And then the last one is giga. And that's times 10 to the ninth. Have any of you guys watched Back to the Future recently and noticed that when they talk about the amount of energy they need, they call it a gigawatt? Because like it's not that long ago. Like I remember when Back to the Future came out, that's long ago that like we just didn't use giga, like we hadn't decided on like a way to say it, you know? Isn't that sort of funny? Like now it's just part of our language, but like it was a simpler time when I was a boy. My first computer was a Commodore 64. That's how much memory it had. 64K. Okay, so let me do an example of how to use this. Let's say we want to calculate how many kilometers are there in 5,000,000. So 5 times 10 to the 6th, let's say micro feet. I've never seen that unit before, but that's what we're going to do. And actually, let me give the abbreviations for these. I forgot to do that. Nano is lowercase n. Micro is the Greek letter mu. That's an easy, if you get really good at remembering what Greek letter is, what they're called and stuff, people think you're smarter than you are. This one is really easy to remember because mu is spelled mu, and it looks like a combination, like halfway between a U and an M, So the other ones you're on your own, but that one's milli is lowercase m, centi is lowercase c, kilo is lowercase k, mega is capital M, and giga is capital G. Okay, so the quantity we're starting with is 5 times 10 to the 6th microfeet. And, well, I'll just write that like this. And micro means times 10 to the minus 6. So I can just erase that micro and replace it with times 10 to the minus 6. And so now we know we're talking about 5 times 10 to the 6 times 10 to the minus 6 feet. Those cancel each other, but I'll just leave it in there for now. And then we know that we used the fact before that 1 meter is equal to 3.281 feet. And then because micro means times 10 to the 6, we know that 1 micrometer, which, no, we don't want micro. We want, sorry, we want kilo now for meters. Kilo means times 10 to the minus third, right? That's what it says up in this table. Who's with me? Okay. Okay, thank you. Okay, so 1 kilometer, 1 kilometer is equal to 1 times 10 to the third meters. And I put those in order. Because we want the meters to cancel. So we want feet. Oh yeah, I did this. I did the second one wrong. Okay. Let's pretend I didn't do any of this stuff. Okay, so we need to cancel the feet. So in the middle one, we have 3.281 feet. Is equal to 1 meter. Okay, so now these feet cancel. And now we want to use the fact that 1 kilometer is equal to 1 times 10 to the third meters. And now the meters cancel, and the units we're left with are kilometers. And now if we multiply this out, can someone calculate that? The times 10 to the 6 and times 10 to the negative 6 go away. So we just have 1 divided by 3.281 times 10 to the minus third. So this here is just 5, and then just divide by those two. 5e6 means 5 times 10 to the 6th times 10 to the minus 6. So with those two together give 1, and then we have the 5 in front. So this all together is just 5. Point 0.001524. And now we're in kilometers. And we can write this 1.524 times 10 to the 1 to minus third kilometers. And that brings up a question that I'm sure some of you have. What about significant figures? How much do I care about that? Because really this only has one significant figure. This one has 4. So what do we want our answer to be? I mean, I suppose really we should only write it with one significant figure. But I'm not worrying about that in this class. Just put a number of decimals that feels right to you. Okay. When you take chemistry or whatever, they're gonna just brutalize you about significant figures. So we'll skip it here. Any questions about that? Okay, so now we're going to go on. Yeah, so we originally started with micro, and I started with this saying 5 times 10 to the 6 micro. But then since micro just means times 10 to the minus 6, I erased the micro and just put in times 10 to the minus 6. But you could do another step to convert from microfeet to feet if you want to. But you can always, in problems like this where you're starting with a prefix, like this prefix here, you can always just erase that prefix and put in the factor that it's equal to instead. Okay, so no, I don't. No, that's fine. Yeah. Although, I mean, since in this case, I wouldn't leave it in a fraction with a decimal in the denominator, you know. So I guess in this case, probably decimals is the only way to go. But I mean, we still have that 3.281 in this one. Uh-huh. I wouldn't leave things in fractions with decimals in the denominator. You know, if you have a decimal in the denominator, just give the whole thing as a decimal. All right. So now we're going on to the first physics topic. That's just sort of a general science topic. Now we're going on to kinematics of a particle along a line. Um, and um, so we have to, this has sort of 3 bits of information in it. The first one is kinematics. So what's kinematics? Um, the way to think of kinematics is it's all the things that describe motion without talking about the causes of the motion. So we're describing motion without dealing with the causes. And by the causes, I mean force and mass of the motion. Um, Later on, we're going to get into the next thing where we combine kinematics with the causes of the motion. And when we include the causes, and that's going to be later on, it's called kinetics. And that's sort of a pain in the butt because those are unnecessarily similar words. But the simpler thing is the longer word. The more complicated thing is the simpler word. Another thing I like to think about, so kinematics is everything that you could calculate from a video of the motion. So, like for example, if you had a really carefully written out grid with distances between all the grid lines, and you had a stopwatch, and you're watching a video of a bug moving along the blackboard, because of that grid of the distances and stuff, and because you're keeping track of how long it takes to get from here to there, you could calculate its position at any time, its velocity at any time, its acceleration at any time. But if you tried to go from there to calculating the forces that were required, you'd have to know more information. You can't get force and mass information from the video. Okay. So we're going to be dealing with, so this is also kinematics. Everything you could calculate from a video, and that includes the position, the time, the velocity, and the acceleration. So kinematics is going to be relationships between position, time, velocity, and acceleration. I.e., so that's sort of another way to think about it. So that's kinematics. The next thing that is included in this description, in this title, is particle. So what is a particle? And I think probably the most common answer that people would give off the top of their head is that a particle is a really small object, but that doesn't have to be the case. Yep. Yes. So a particle doesn't have to be small because, like when people do, and you think particles are small because when people say they're a particle physicist, what they mean is they're doing calculations involving subatomic particles. And those are calculations they use are because they're tiny, tiny. People also use particle analysis to determine the relationships between planetary positions and planetary motions. And obviously, like planets are gigantic. So what is it that makes something a particle? Well, a thing itself is never a particle. Remember that treating something as a particle is a choice we make. The thing isn't that way itself. So we use a particle model for an object if we only care about the motion of the object's center of mass. And if we only care about the motion of the object's center of mass, that means that we don't care at all about the orientation of the object. So we don't care if it's spinning or anything like that. Okay? Care about changes in the object's orientation. And so now you can imagine the same object, sometimes a particle, it depends what you want to know. So, like for example, if you're doing a calculation involving a baseball and you want to calculate like how far it flies if I throw it with a certain initial velocity or whatever, we don't care about whether it's spinning or whether it lands upside down. We just want to know where the center of the ball is. So we would treat it as a particle. Now, if you wanted to calculate where's the Rawlings logo or whatever when it hits the ground, then you have to take into account how fast it's rotating. Orientation matters, and we wouldn't use a particle approximation for that. Okay, same thing with planets. Like if you if you just want to know where Jupiter's going to be in its orbit on a certain date, then a particle approximation is fine. If you want to know where the spot of Jupiter is going to be oriented at that time, then you can't use a particle approximation. If that particle approximation is enough for you, so if you're using the particle model, the object is treated as having no length dimensions, so it's infinitely small, like a little point-sized thing moving around. Although it still has mass. And so then when we say, what's the position of the particle? Position of the particle is where its center of mass is, the location of its center of mass. And then along a line, well, it's pretty clear what that means, but what's the point of starting out with such a simple description? So the key thing here, the simplification that we're going to take advantage of for a particle moving along a line is that at any instant, there are only two choices of what direction the object can go. So if the object is moving along this line here, and at this instant it's here, we can only go this way or that way. Okay? That's not going to be true once we start doing things in 2 dimensions, because then it can go this way or this way or this way. It has infinitely many choices. Okay. So in parentheses, once we get to 2D motion, there are infinitely many directions. And what we're going to see is that the fact that in 1 dimension, moving along a line, there's only 2 choices of where to go, means that we can represent direction with a sign. Okay, we're just going to assign one of these, and it doesn't matter which one. Let's say that one's negative and that one's positive. And then if the thing is moving in the negative direction, we know it's that way, and in the positive direction, it's that way. Okay, so mathematically, this is an easy way to represent directions. So starting with motion along a line makes representing the directions easy. Once we get to 2 dimensions, that's not true anymore. because there aren't infinitely many signs. There's only two of them, positive and negative. So once we get to 2 dimensions, we're going to have to invent a whole new mathematical object to represent directions. And anybody know what that object is called that we're going to use? Vectors. Have you heard those before? Done those a little bit in math? So when we're doing motion along a line, we have plus and minus to do our directions, and that's all we need. Once we get to 2D, we're going to introduce this mathematical thing, vectors, and we're going to have to use those vectors to define directions. And we're doing kinematics, so that means we have to define position, time, velocity, and acceleration. And so now I'm just going to go through these sort of one by one and talk about the relationships between these things. I'm going to start with position. So right now, everybody in this room is in a location, right? And that doesn't have anything to do with whether someone is doing physics about it or not. Like, you're there in a location. What does it take for us to put numeric value on that location? Because that's what a position is. So what would it take for me to put a number with that spot, a number with that spot? So at a given location, what does it take to express that location numerically? And when I say this, expressing this location numerically is what we're talking about when we talk about position. Well, the first thing that it takes, and let's say I'm saying this, we've already decided we're going to do our calculations in meters or whatever. We have a length scale. But first it takes a default location that we're going to call 0, a reference location. And second, it takes choosing which direction is positive. Okay, so let's say, so here's the table. Here's the item, make your femurs extra long so you'd fit under the desk. I'm mostly just drawing this picture the rest of class. Okay, here's you. Sorry about your hair loss. Okay, so what does it take to represent that location numerically? Well, what it takes is we have to say, and here's your center of mass. So this is what we're going to represent. Let's say that the line that you're free to move along is like this, okay? because this is motion along a line. So we're going to choose a point that's going to be our 0 position. So I'll write that as an O, like origin. And then we have to choose along this line which direction we're going to call positive and which one we're going to call negative. And it doesn't matter which one, so I'm gonna choose positive this way because it's the opposite of what everybody normal person would choose. And then now that we've chosen the 0 position in the positive direction, we can just count off the distance. So let's see, what's the distance? Let's say that's 1 meter, 2 meters. So let's say it's 2.5 meters in the negative direction. So in the negative direction from 0. And so we would say that the position is equal to, what's your position if you're 2.5 meters in the negative direction from 0? What's the numeric value? Negative 2.5 meters. Okay. But if we didn't, before we make that choice as 0 in the positive direction, there's, we don't have anything. So we have to choose that reference. Let me say one more thing before you go. Sorry. Units for position are units of length. And so that means that the SI units are meters. Okay, that's all.